Hello, everybody. I'd like to introduce Stephen Rowe. He's going to be talking about physics unit and why you want to use Raku in order to make use of this module. Stephen?
Thank you, Todd, and good morning and welcome to everybody. Appreciate you taking time to join the session today. So yes, indeed, this is about physics unit, which is a module for Raku. For those of you who don't know me, I'm Steve Rowe, also known as P6 Steve. And P6 started around Perl 6, as you can guess, but it also was a pun on physics, P6, if you can get what I'm saying here. And somebody went and changed the language name on me. So there you go. I kept the name for now. Maybe I'll think of something better as life goes on. So yeah, my philosophy here is, anyone who's dabbling with Raku, who's working with it, we're all on a journey. We're all learning something new, and we're kind of following the footsteps of some, really smart people. For the sake of argument, I don't count myself as, as a smart person in that regard. So I don't come from, a language architect or, language designer. I don't come from a compiler implementer and so on. I'm not kind of a deep developer like that. I'm more in consumer land. For me, it was a step up to go from just coding. I mean, I spent many years making money as a Perl developer, but then stepping up to actually taking on writing and distributing a module was a step change for me, bit of a challenge. And I chose physics unit for the various reasons we'll see. I think it's a great, first of all, it matches my experience, my background in being a physics major. It's kind of my interest. And also I felt it would be a great way to bring all the different bits of Raku together into one package and see how they could all play together. So yeah, so physics unit for Raku is a rewrite of physics unit for Perl 5, so standing on the shoulders of the guys that built that. You'll also know that there's a physics scalar module over in Perl 5 world. I've actually recast that as physics measure for Raku because scalar is a concept in Raku, and I didn't want to create any more confusion than I need to. And then additionally, an extra bonus today, I'm going to talk about physics constant, which is a new additional adjunct module, which is kind of a wrapper on math constant to bring in, the constants you need, like the speed of light, like Planck's constant and stuff like that. They all have units and they all have dimensions, so we can use physics measure and math constant, bring that together as a wrapper and make it sing. So yeah, so when I think of a journey like the one we're on with Raku, it's about, I think, for me, it's about really interesting ideas of how people might use a new language in a different way, perhaps not a complete revolutionary different way, but an evolutionary different way. And so I'm a user of Raku, and I see that the users of my modules, they're kind of my users, and usually that's going to be scientists, right? So I'm kind of picking out my scientists here from that wider community. Although units are used, in different places too. They're used in education, they're used in engineering, they're used in a lot of, in business. So it's scientists is just, the main focus, but there's a bit of peripheral around that. I'm also thinking about how people might want to use a module like physics unit or physics measure. There were basically 3 different ways that I was thinking that, could be of value to somebody who's primarily a scientist, but who likes to do coding and programming as a way to accelerate, it's a bicycle for the mind, as it were, for their science that they're doing. And the first way, and I was kind of encouraged to do this with feedback from my first release of physics unit, was to use the capabilities of Raku to really transparently mutate the language to put SI units and SI unit prefixes directly there and just make them super easy to use. So, without talking about the concepts too much, this is how it looks when you write Raku with physics unit. We'll see some examples later on. So what I have is my $L equals 1 kilometer. And what that's doing behind the scenes we've populated, if you use the unit postfix sub-library, sub-module that I published, then that populates your code space with a whole bunch of new postfix operators. And what those operators come from is the SI prefixes, so C for centi, M for milli, K for kilo, and so on, and the SI base units, so M for meter, S for second, and so on and so forth. And it creates a whole bunch of postfix operators. And when I employ them, I basically take my number, it's a real, it needs to be a real, and then I just postfix it with that combination, so kilometers or milliseconds or whatever you want to use, and that then will create an object and will assign that object to my variable as the default part of the declaration there. In this case, my object that's going into L is an object of class length because it's kilometers. So physics unit is smart enough to know that if there's an M in there, then that's a meter, and if it's a meter, it's a length, and it makes it a length type. And therefore, we'll see later, when we start to do operations, how that type is then used to automatically evolve, to calculate the units part of the result. In fact, you can see it right here on the screen in the third line. So the next thing I have is time equals 1 millisecond, same concept, it's time in this case. And then, I could do some math. So I'm overloading all the basic arithmetic operators, plus, minus, multiply, divide. And in this case, my S equals L over T is 1,000,000 meters per second. And what is S? Well, it's the speed. So physics unit knows if I'm doing math on one or both of the operators around this infix, so the operands around this infix operator, one or both are a measure type, then it knows I'm going to do something special, and I'm going to be thinking about how to recalculate the speed of the result. Sorry, the unit dimensionality and the unit, the class, therefore, of the result, and creates me a new object, in this case of class speed, and puts it into S. So great, so that's use case number one, just very simple, inline, get those SI units and prefixes, and do math with them. Okay, so what about another use case for physics unit? So here I think about, from time to time, we still live in a world, particularly when we're talking globally. You probably hear from my accent, I'm from the UK. So I live in sort of mixed mode between metric and SI units, particularly when I'm at work and I'm doing science and engineering type calculations. And the things we use in our daily life. So we use miles per hour, we use these imperial units, we call them. There's similar in the US, of course, feet, inches, those things still exist in the wild. And I still think they're very important for any comprehensive unit module to be able to provide really handy conversions to and from different unit types. So this for me is the important use case number 2. So you can see here I've got my F, my $F equals $L.in. So in is a method defined by physics unit, and then I give it my target conversion, which is it's a string of FT, which is feet. So I get resulting from this, I get a new length unit. But this time, instead of it being 1 kilometer, that's the L from the previous slide, so it's 1 kilometer, is now 3,280.84 feet. So you can go back and forth, and we'll show some of that later. And you can do this across all different types of, there's things like temperature in here and forces and all kinds of good stuff to play, and volumes and areas to play around with. So just a very, very handy tool. Now, within physics unit, I also define the comparison operators, and specifically, if I'm going to compare F and L, if I were to do that using the standard, not overloaded Raku version of CMP, then it would say different. I guess it's different, right? For not same, but this would be different. This would fail. But when I'm comparing, is 3,280.84 feet the same as 1 kilometer? Well, in the measure land, it is. That's the same thing, right? It's the same physical measure. So it's coming out as the same when I compare the two. Okay, then we look at use case number 3, which is, I term this as composition. So often, if you dig around in the SI units, for example, you have this idea of base units and then derivative units. So something like a kilogram or a meter or a second is a base unit. And I think there are 7 or 8 base dimensions defined within SI. And then there's a whole bunch of shorthand for these derived units. So in this case, I know that 25 kilogram meter squared divided by seconds cubed is actually 25 watts. So I can put that definition string and the number into my Raku code now. You'll see for the first time here we have this little Libra Unicode operator. This is a special operator. It was inspired, my inspiration really came from the atomic integer operators that exist around concurrency. And I thought, yeah, this is a really neat idea because, I can define a power, I could take my normal way of saying, my u equals unit.new, pass it in the string, and then my p equals measure.new, value arrow 25, unit arrow my unit that I just created. But that's quite a lot of code. If all I want to do is just put something into a variable here and give it a default. So this Libra operator, I created it as a really handy shortcut for, during declarations, to create default values from a string. And then physics unit will then go in and it will pluck in fact, measure plucks the number off the front, and it hands the rest of the string to physics unit that will then pass the rest of the string. It figures out, it knows that this set of, this expression, this unit expression is actually a derivative unit under SI, and it's the unit W or watt, and it's a unit of power. So it gives me back P, there's 25 watts as power. So I can use that throughout. We saw, there is a quicker way to do my time equals 10 seconds, but if you don't want to use the postfix, submodule there, you can just use a string version here as we got it here. And again, as before, I can do unit math. So my E equals P times T gives me, power times time is energy, so 250 joules in this case. And one last thing around composition, we didn't forget that what the definition of P is, and we can always, so the SI preferred way of expressing or printing out a value and its units is actually shown here in the bottom right. So there's a few things around the SI preferred method, and this is the kind of formal way of doing it in the base units. They also allow you to do it in derivatives, which obviously we do also. So here we've got m squared, meter squared. Of course, it's a 2 as a superscript. So what a great fit, can now use superscripts within Raku, so that's cool. I've got this kind of midline dot. There's probably a formal name for that, but it's not a full stop type dot or a period type dot. It's in the middle of the line. So that's a Unicode symbol. And I can just therefore easily create this pretty method, which is, again, comes with physics unit and lets me print out my unit in the SI preferred way. And we've got a couple of different kind of friendly ways of printing stuff out to match the different requirements people might have. Anyway, that's the Libra operator in a nutshell. There'll be a little bit more on that later. So it's also, I think, because we're doing quite a lot in terms of overloading the functions, we're overloading a lot of PostScript operators, then I quite like the idea of having some unusual symbol that is recognizable dotted around the code that lets people know I'm not just in vanilla Raku now. There might be some odd things going on here that create behaviors I didn't anticipate because someone way up in my software has put use physics method, use physics unit. So that's it for my use cases. I think those are 3 complementary goals around any kind of physics unit module that is required. I think it's also important that this be delivered in a combined way on a single infrastructure, so I can have the same set of classes. I can mix the classes and use the type constraints around classes independent, across all the different kinds of use cases that I might be using. Right, so that's what I believe Physics Unit is trying to do. You're welcome, by the way, to go to GitHub. The details will be on the end here. Put in any kind of requests and issues that you might have. You might have a whole other class of uses that you want to do with it. I'd love to see that. I'd love to have that kind of feedback and encouragement of where to go next. So then I thought, well, okay, we want to do all these things. So why Raku? Why not do this in Java? Why do we need to do this whole new language, and what would be different about it? So I started, as I started working through this, it became very clear to me there's a lot of things that Raku brought to the table, starting back in 2015, but in the last few years, more and more, are pervasive and really useful for someone who wants to get more out of their, scientist type of person who wants to get more out of their programming and their coding. So Unicode, I think it's just perfect for the kind of scientific equations and formulae that people need to do. I think classes and types within Raku, that class model, is a really great way to come in and extend that with classes of unit, classes of measure that can really fit in very neatly and be a good citizen within that wider class type universe that Raku defines. Object-oriented, I kind of separate this a little bit from classes and types. So the first bullet here is more about the class is a type. So therefore I'm going to be doing type checking and using types to drive some of my algorithmic decisions. And then the object orientation, I think you'll see it later, is about how can I compose together code if I'm a scientist that does useful stuff where the scientist, I can use object orientation to do my notations and produce my results in a clearer and more comprehensible way. Then foo here, apologies for the reuse of foo, but obviously this is functional operator overload, so we're going to overload those basic arithmetic operators and a few others within Perl and within Raku. And then another couple of really cool things about Raku is rat math. So using rationals as a default mathematical real type, very, very useful, particularly for round tripping on unit conversions. And then finally, grammars. So grammars comes into this in a big way too, particularly in passing those unit expressions. And I think Raku is having those grammars built into the language. It really turbocharges what you can do, with your coding and particularly in creating a module like this. So let me just kind of give a bit more flesh on those bones there. So Unicode, here's an example of why a scientist might want to do Unicode. So let's say I'm a physicist and I want to do a little bit of simple math on the wavelength, frequency, energy of a photon. Now my normal way to do that is I know that lambda is the wavelength of a photon. So I can just put in my / lambda is 2.5 nanometers. It's as simple as that. Now, how do I get to my frequency? My frequency is usually represented as this funky V. It's a Greek letter nu. So my nu equals c. As you probably know, c is the speed of light, 3 × 10⁸ meters per second. And I need to divide that by lambda. So c comes in from our physics constants module. So I can use it right here in my calculations. So I get my nu equals c divided by lambda. And I can then immediately say nu is, and then convert it to petahertz, just under 120 petahertz. And then finally, what else can I do with this kind of approach? Well, I might want to get my energy of my photon, which is my Planck constant multiplied by the frequency. So energy of photon is in attajoules, just under 80 attajoules. So there, I can be hacking away on my little, calculation notepad here as a scientist, quickly getting handy conversions and stuff and doing calculations, checking order of magnitude type stuff. Then I'm getting my you know, I'm doing the right thing and getting sensible results out of my experiments, and also having that nice Unicode to present back my results in if I want to have some kind of shareable, you know, readable stuff that my peers can understand. So I thought Unicode is just a perfect fit for this kind of module. Okay, so let's look at types and classes. By the way, this little blue arrow here is meant to draw your attention to the bit of my quite noisy slide that I'm talking about. So within physics unit, we have about 230 built-in units. So a small example here, they probably represent, I think there's about 25 to 30 different classes. And so for example, my volume, my V is 7 cubic yards. I don't have to specify it's a volume that's induced from the string expression passing the grammar does. I can put my volume in meters cubed. There we are, 5.352 meters cubed. My ds dt is speed over time. So speed over time is an acceleration. Oh yeah, I've got 70 miles an hour. I haven't forget that we drive around our cars in miles an hour. So we might want to know that from time to time. I can do forces. So I can see my forces, comes out of this set of base units. It's 27 newtons. I can handle energy, I can handle power. You've seen a little bit. I can multiply power by time, and that gives me back an energy. So the class declarator creates a compile time construct, that's then created into the type object. And that's really important because it means we can catch any errors now where somebody tries to add a speed to an energy. They're going to get a nice little error there, and they know that's something they shouldn't do. And so a scientist is going to get the kind of error checking and controls that will benefit all of us in general. Now he's getting it in his scientific calculations and his world, or her world, or their world. Great, so let's talk about the object orientation and how this fits in the wider Raku 00 world. So those of you who've been studying their Raku, I'm sure you know this is the Raku standard object map. It's a great little graph, actually, or object graph, I should say. It's in the documentation. I use it quite a lot. It helps me really figure out, how things work. So mu here right at the top, everything descends from that, inherits from that, and any, and then cool, and so on. So everything down to sort of the rat and fat rat on the left here, and then int num string, everything above that line is all standard Raku. I've just colored things that I'm using. So physics measure, physics unit world is red. So you can see down here, well, first of all, here I've got physics unit, and physics unit is going to be, it has a string, which is that definition string. It does a whole bunch of other things with it. Then all of those different unit types are, how do I describe it? Type length is unit, right? So that's how that typing inheritance is done. So we only have to put all the methods and all the code in the parent physics unit class. Physics measure then has two things in it, roughly speaking. It has a value, which is a real, so that's just the red arrow here, and it has a physics unit, which is a physics unit. So we just bring those two together as two has attributes of your physics measure object. So now I have 25 meters, for example. Other things that are relevant then to physics measure and physics unit around this picture are we can use everything within the measure is a real. So it means we can use both kinds of rationals, rats and fat rats. So you can have kind of infinite precision math if you want. And a lot of scientific stuff goes way to the very small and way to the very high. So that's extremely valuable for this world. We also have duration as a real. So that means, duration in Raku is the difference between two intervals. So for us, when I talk about time is 10 seconds, and that's a time class, then the value in that measure is a duration object. So that 10 seconds object has a value of 10 duration with a value of 10 inside it. Excuse me, I hope I explained that right. So it's encapsulated properly so that I can then use that duration with all the other great date time capabilities of Raku. So I can say, how many hours is it between, train leaves station traveling at 37 meters per second and gets to, Chattanooga, which is 47 miles away. I can use, the real world date time capabilities within Raku to do that in a coherent way. And then finally, at the bottom right here, we have in purple, just to kind of, it's a mix of colors. And basically the green here is math constant. So JJ Morello, very nice module called Math Constant, has a whole bunch of physics constants, but purely as numerical values in it. So rather than create a second copy of that in the Raku module world, I wanted to reuse that. So create a physics constant, which is basically a wrapper on math constant that takes all of the physical constants out of that library and wrappers them, makes them into measures. So we basically say, c is the speed of light. The value of that came from math constant, but the units is meters per second. So that's the little job that physics constant is doing there. And obviously, great thing about Raku again is lots of constants have, naturally are a Unicode representation like Planck's constant, and many more. And we'll see a few more of those later on in the talk today. That's great. So some great cool stuff already coming from Raku. Now let's look at my operator overload. So yeah, basically taking all the the basic plus minus, multiply, divide, and overloading those. So if the right or the left or both is a measure type, I pick that up and I do special stuff with it that handles the unit part of the measure and returns back a sensible result. So here I can do I can multiply two lengths to get an area. I can divide distance by time to get a speed. 1 over a time is a frequency. Stuff we kind of seen already. You need in terms of having a consistent set of tools in the toolkit. You also need to do this for things like volume, for example. I'm going to get a volume or an area, then I want to be able to use powers. So I've got up to 4 powers and 4 roots supported in physics constant. You might ask, why do I only go to power 4? Well, the most challenging thing I can think of is Boltzmann's equation, I think it is, which has inverse power of t to the 4 in it. So I think in practical terms, that gets us all the tools we need. If anyone comes up with wanting more powers in here, then we can do that. So it's both powers and roots. So I can go from, in this case, from length to volume, and then I can go back from volume to length. Great. I mentioned rats for round tripping. Here's some real examples from my tests. So here I've got temperatures. I've got degrees centigrade or Celsius. I've got kelvins. I've got degrees Fahrenheit. So you see, if I were using a language which did not default to rats, then whenever I did some kind of simple calculation and just factoring a value, I might, well, if I do that twice, I'm converting out and converting back in again, I would quite likely end up with 38.9997 or some kind of near miss. But of course, the round trip really is 39. That's what I put in the first place. So very valuable capability in Raku as the default that makes sense to people who are using numbers in their day job. And you can imagine, I'm a doctor, okay, that's kind of not quite a scientist, but these are quite useful tools for things like medical research and so on. And you need to be able to do predictable things with the results. And then the last cool thing about Raku that really worked here is grammars. And it took me a while to get my head around grammars, I'll be honest. By the way, it took me about 2 years to write physics unit. And what you see now is a complete rewrite of the first pass, because the first pass I was really learning Raku as I went along. So it's quite a lot cleaner. It's probably not perfect. But anyway, this is my grammar. This is actually the entire grammar for the unit expression parsing that we need to do. And it came in at approximately 20-25 lines, and I even have blank lines in here to make it readable. What an amazing tool! I mean, it's like completely an order of magnitude more powerful than what you had in Perl 5. And I'm a little bit ashamed. I did a blog article the other day that compared the Perl 5 version of this, which is in fact a very tidy rec descent parser written in Perl 5. I think that version was 215 lines, if I remember right. So this is something like a 10x reduction in the amount of code that you need to write and maintain. And it just goes really naturally with the object orientation as well. So you create a little stub object as you start here, and then you can, as you hit the actions about another 10 lines, you just build up and load up the different things as you go through and pass. It's really nice to have object orientation and grammars side by side. One very strong piece of advice: I really strongly encourage anyone who's going to get to grips with Raku grammars. It's commented out here because it's I only use it for debugging, but use Grammar Tracer is absolutely fantastic. Without that, I would be completely lost. It's just a superb tool. So great. So hopefully that's given a little bit of view as to how those different bits of Raku kind of come together here, and how it makes physics unit be different in Raku land than it was ever in Perl land, or could ever be in Java land, for example. So let's see it in action. I'm just going to pause my slideshow here, if I can work out how to do that without disconnecting. Okay, I think I did that okay. And then I'm hoping that you can see my screen here. Yeah, that's cool. I'm going to make that a little bit bigger. Hang on, I'll just go to dark mode. I'm just living in fear now that dark mode's going to kill my presentation when I get back to it. Hopefully I remember to turn it off again. So this is my little summary synopsis for physics unit postfix. So basically, when I want to write with these kind of units within my code here, then I'm going to have a bunch of postfix operators defined in my language. Let's do a new one. You see already, equals 17 centimeters. Say, this is where I prove I can't code for toffee. Excuse me. Can't even find the escape key. Right, and then I'm just going to run that down here in the box below. I'll make that a little bigger while it's running. So apologies if you get a slightly different idea of speed and perspective here. We'll have some words about performance at the end, but I think for the kind of use cases, Raku is very good for balancing performance against capability and functionality here. So you can see I've got my 17 centimeters down here at the bottom. Maybe I can do something else, maybe add that together. I'm not going to do too much coding here because I don't want to run out of time on the simple stuff. I think you can see everything working together. We've got conversions in here as well. So I'm using use physics measure. That brings in the measure object types. And then I'm using unit postfix to bring in that whole set of postfixes. So one of the things just to mention here, the way that I do that is I have my list of about 17 prefixes, and there are about 7 or 8 SI base units. So if you multiply that out, I'm actually bringing in something up to 600-ish postfix operators into my language. So there's quite a lot of mutation going on. So I think one of the things I want to do going forward is just make that very crystal clear of what's being imported in, and give some controls over that, through the labels. But here it is. It works great for now. That's why I'm kind of mentioning speed, because I think if you want to use all 600, obviously it's going to be a lot slower than if you're just using macroscopic type, base type measurements. Time and distance and so forth. Great. So hopefully that gives an idea of the unit postfix in action here. Another one I wanted to share with you was the excuse me, I'll just get out of here. I already typed the IM. Let's try synopsis unit. So I just want to show you what the physics unit looks like and the kind of flexibility that has. If I run that, it'll give us a little bit of real output as well. So here, basically, I can formally define units. So I can have here FG unit new equals, it's a furlong per fortnight. I can define my own unit. I've got built in a furlong and built in a fortnight. Those are just decisions to put them in. But you can extend what's in the base unit module with your own definitions and your own expressions and give them your own names and so on. And then here, I can just see a little bit of confirmatory, what did I create as I went running through my little synopsis here. So hopefully that gives you an idea. And here's that pretty printing coming on at the bottom also. So this is what a unit object actually looks like and what's inside it. So we track the dimensionality. There's a mix in here, so it's a good production use of the mix capability within Raku. My goodness, I forgot to put that into the benefits. His Matt will be hopping mad with me, I guess. Sorry about that. Fine. Okay, cool. So far this is just standard command line stuff. Something else I've been working with. If I can find my right window here, it's over here. Just going to bring it in. Is something called. You may well know this. Something called Jupyter. So Jupyter comes out of the Python world, dare I say, but I really like it. I think it's a great tool for helping, let me say, amateurs get access to compute capabilities with very little knowledge about setting up all that command line stuff and so on. So rather than go through my synopsis for physics measure on the command line, could have done that. I thought I'd just break it down and show you an action here within Jupyter. So Jupyter, just a little bit of a guided tour here, comes in these cells, and then it's actually running. So some great work from, I'm just going to probably credit the wrong, Brian Duggan, to produce the Raku kernel for Jupyter. What a fantastic project that is, and I love it, and it's going to be really helpful for me in my work going forward. So I can go into a cell here. This is cell number 1. I can run the cell, and then that's going to, so what I'm doing here is, you see I'm now bringing in that Libra operator, so I can define units and objects in a formal way within physics unit and physics measure. I've just got a lot of things running here, so it might be a little sluggish. Tell you what I'm going to do is I'm just going to see if I can run through here. Okay, let's not worry too much about that. I'm sure you trust me that these answers that I have in parentheses here really do happen, and they happen on a reasonably powerful machine. Everything happens within a couple of seconds. So this synopsis kind of works through the things we spoke about. Here's some examples of a date time instant within Raku, and then a duration being a difference of 2 instants, and assigning that to time. And then I can just have natural terminology. My time is 2 hours if I'm applying physics unit and the Libra operator. Yeah, and I think we covered most of these so far. And there's lots of different comparison operators also that you can benefit from. So what I showed was the kind of the obvious one, which is things are superficially different, but physics unit knows they're really the same under the hood. But you can get to numeric comparisons and unit comparisons with the string comparators or the numeric comparators, as you would naturally expect. So let's see what else I've got in my bag of tricks here on Jupyter. I wanted to start using my physics unit module as one of my users would, so I could really get to grips with, does it do good stuff? Is it really useful in the real world? So I've got another notebook in here called Rect Math. It's short for rectangular math. So I'm bringing in a couple of new concepts here. First thing I'm bringing in is there's a library called Math Polygons, something that I created. It's a simple module, and it basically takes the SVG polygons library that's already exists, and it wrappers on that to give us some polygons with mathematical properties. And I'm going to use physics measure as well. So now I've got my math polygons in my code here. I'm just going to do a little bit of tweaking. So I'm going to basically localize my M drawing. My measure drawing is a polygon drawing, but I just inherited and overrode some of the attributes and methods in here. So I want to have actually my scale be a real unit, like I want my scale of my drawing to be meters. This is going to give us an SVG drawing in a second. Then I've got my endpoint. So my endpoint is just like my point class, but it has a length instead of just a number. So now I'm bringing my measure type of lengths, putting it in mixing it in with Raku objects. And then I'm going to have a override the scale method as well, because I'm going to do scale things back according to putting my point into the right units as defined in my drawing. It's doing a similar thing here for my rectangle. So my rectangle, as you can imagine, it's got an origin, it's got a width and a height. So these are an endpoint and the length and length, as you would expect. So these are kind of objects that I think a scientist or somebody studying physics or engineering could easily get to grips with and play around with, and really use object-oriented coding within their same discipline, within their discipline. Okay, now, so I'm going to bring in physics measure, use physics measure. I'm going to start using this. So I've got my XY width height, so my origin in meters, my width in 120 meters, my height is in meters too, but my S, which is my side of my rectangle, is going to be 100 feet. So I can start to mix units together. I'm going to declare some real objects. I've got a real rectangle and a real square. And then I can go ahead and get some information about my objects. I can use the simple accessor, attribute accessors to simply print out some stuff about them. And then I can go ahead and draw my drawing. I've got my rectangle and my square here. So it's not quite three-dimensional movie style, rendering right now, but it's actually allowing in a classroom setting, for example, or a write-up session to really mix real world metrics and measures, real units, in with graphics and in with more elaborate objects. So I felt pretty pleased about that. As you might expect, I've got another example of that, so I can do that for triangles as well. Triangles is a little bit more intricate. Okay, and what I've got here is a triangle with my M triangle is an M polygon, has 3 sides, obviously, and that has an apex point and has a length of side. So this is actually, I didn't specify it here, mea culpa here, but it's actually an equilateral triangle. And one of you'll notice before I had the method area for my rectangle and my square, that's dead easy. But triangle, you have to do a little bit more measure math to take that apex, calculate the height of the triangle from the side, and then do this measure math. So that was needed to get my little area calculation here. Then I can make one, and I can give myself, I can actually calculate the area right here in a really friendly way. And now to draw them. So here's my triangle object. Yeah, so what this started me thinking that there's a whole set of math type operations around sines, cosines, triangle, identities, Pythagoras, different types of triangles, and the relationships of the angles of a triangle and the sides of a triangle. So don't forget, within my physics measure, I support angles like radians and degrees, minutes, and seconds, in fact. So that's something that's another area for elaboration here with the module. So really fascinating stuff, what you can do when you get these tools in front of you. So great. So that's basically all of that you get out of the box with the by installing with Zeph. I wanted to just give a little bit more fun here today, just as we wrap up. Oh, before I do that, so I mentioned Brian Duggan for the Jupyter work, also JJ for the great work he did on math constants. So here I'm using physics constant that knows that it will use math constants, and then this is the kind of thing that I can do with constants. So I've got Faraday's constant, fine structure. They all have a long name, which is JJ's definition, and also often they have a Unicode kind of shortcut name, or C is not Unicode, but it's the short name. Again, it's all the same names that JJ had. I'm just layering in whether that be dimensionless, or if it's permittivity, I guess this is Henry's per meter. And you see the example I gave earlier. And these are all the physics constants that are built in out of the box, just ready to use, and all the shortcuts. Right, so let me go back to my, here. Yeah, I want to go back up. So the thing I mentioned earlier, I ended up rewriting my first attempt. It took me about a year, and I rewrote it. It took about another year. It's a heck of a lot better. But one of the things that made me rise to that challenge, I thought, I want to do, there might be some situations where, let's say high school students, they want to do calculations on volume of quantity of liquids. So liters, sure, we have that. That's a kind of a pseudo SI unit. But what about, old-fashioned units that I used to have as a kid? And I started thinking about barrels and pints and stuff. I thought, yeah, I want to have a firkin, represent a firkin type. I don't know if you guys know what a firkin is. Anyway, we'll soon find out. A firkin is, a barrel contains 36 gallons, and that's 4 times as much as a firkin. So a firkin is a quarter barrel. And if you've ever run a real LPUB, which I did in my youth, you'll know that a human being can lift a firkin. You can't really lift a barrel without being very strong or having a helper. So I thought, I could not work out how to add in this firkin type with the right conversions and stuff in my first bit of code. I couldn't even maintain it myself. It was too complex. I had to simplify it and really boil it down and refactor it to make it, much more streamlined and maintainable. So here, bit of fun. My weekly limit is 14 alcohol units. I would never exceed that. My firkin is 1 firkin, and my strength of beer is 4.4 alcohol by volume. ABV is a unit, of course, so is alcohol units within physics unit. These are very important units to many physicists, I can assure you. And then I can work out that my week's supply, how many weeks supply 1 firkin will give me at my weekly limit. So 1 firkin of beer contains just under 41 liters, and that's 13 weeks supply. So there we are, a bit of fun. So you can have fun with physics units too. Cool. Let me go back and see if I can remember to turn dark mode off. I'm just going to toggle it off because I really don't want to mess up my slides. Hopefully that is going to work. And then I'm going to share my slides again just to do the wrap up here. Just want to make sure I'm not going to repeat some of these things. Okay, that's where I want to be. It's not showing on my screen yet. I'm just going to give it a second. I don't know if I've done something crazy here. Oh, we have, yeah, here it comes. It's just a lot. That kind of explains why things are going a little slow, is there's so many things running on this little, I have a very thin MacBook. It's doesn't have a lot of processing power. Usually with Zoom running and everything, it's just bogging down a little bit. Oh boy. Okay, I think we got it. So yeah, just to sort of run through to recap on those various pieces of Raku that really helped us out here. It was Unicode, it was classes and types, so doing that type checking and bringing that error support in for our scientist users. It was being a good citizen in Raku 00 world and using Raku 00 properly. It was about, you know, overloading those operators in a nice transparent way. It's about getting the full benefit of rats. That's an awesome feature. It's great. And then finally, you've seen how grammars have made this all possible, and it would be a lot harder, heavier lifting without grammars. And of course, sets, mixes, and other great stuff in the kit bag. So please, I would strongly encourage you to go ahead and play with this. I'm not sure whether vanilla Zeph install physics measure is going to get you the very latest version. I just released that in the last 24 hours. So I recommend you use Zeph install, you know, my GitHub URL. And I also recommend you do that with a verbose. It just takes a little bit of a time for first pass compile on this. So I did have to do a little bit of basically object building and caching. So I'm basically using the benefit of the pre-comp to make sure you have, you know, sub-second performance for all the calculations you might want to do in the real world. But the cost of that is it takes 5 or 6 minutes just to install and do first pass. So if you use verbose, you can see the stuff actually going on for most of that time. And this is all the great things you get. You know, you get a really comprehensive set of units and measures, class types that smoothly extend Raku 00. You get no loss of fidelity with round trip conversions. You've got Unicode very naturally throughout. You've got that postfix notation, very convenient. Grammar notation for composing more complex, unit strings out of base SI units, and you've got that whole world of SI, US, and imperial units you can use for conversions. What next? So I mentioned about, you know, a little bit more fine-grained control over what you import when you use unit postfix. I'd like to add in errors, relative and absolute. Those with sharp eyes might have noticed I had to manually refine my output in petajoules, I think it was, or attojoules for some of these calculations. I'd like to automatically, have a setting to let you automatically normalize with the right prefix, so you don't have to kind of guess and then get it right and then fine tune. Love to be able to integrate with other modules. So speed, for example, is, you know, in physics, it's a scalar. You know, velocity is a vector, so it has a unit, a value, and it has a direction. So we need to somehow find a way to use math matrix to make that kind of thing work. Performance, yeah, I think it's good enough. I had to do quite a lot of work to tune physics unit, physics measure. I would just kill for macros. I hope somebody's working on that. I'm not sure it would make things faster, but I basically have to self-generate, you know, 600 something units for that first compile pass, and they're all in my source code, and that just a lot of lines and a lot of overhead that and maintainability issues that I want to avoid in future. And then for me, it's about doing more, you know, use Jupyter, get it out there, do a lot more physics textbook type examples, and start to see if we see if we can stir an interest with our, you know, scientific buddies. And, you know, perhaps reach out to National Physics Laboratory and the other people who are true owners of the standards, and see if they can get some fun out of using Raku in their worlds. So thank you very much indeed for your time and attention. We've got a few minutes left. I think I'll defer to Todd in terms of you know, how much time he wants to allocate for switching over.
You're actually over.
Session. I'm over time. Excuse me then. Thank you very much, everybody, for your attention here and your interest today. Just drop me a line, p6steve.com, and take a look at any of these, you know, these GitHub, places to give you these GitHub repositories for more information where you can raise issues and questions and so forth. Have a great conference.
Thank you, Steve.